Hello everyone. I'm Putra. Today, I'll be walking you through a fascinating concept in graph theory called book embeddings. Imagine you have a complex network of points and lines that are messy and crossing everywhere. In a book embedding, we fix this by placing all the points, or vertices, along a single straight line. We call this line the spine of the book. Now, the interesting part, the connections between these points, known as edges, are drawn as half-circle arcs. These arcs are placed on different pages, or semi-planes, sharing that same spine. The golden rule? Arcs on the same page are not allowed to cross each other. Our goal is to find the minimum number of pages needed to draw the entire graph cleanly. This is what we call book thickness. It's like organizing a chaotic web into a perfectly structured book. Let's see how it works.
Hello everyone, good day. My name is Putra Natanael. Today, I'm going to present a fascinating topic from graph theory titled Book Embeddings of Graphs. As you can see on the screen, our main focus will be on linearizing complex network topologies into structured layer formats. In this presentation, we will explore how we can take a chaotic, messy network of nodes and edges and systematically organize them into a clean, layered layout resembling the pages of a book. Without further ado, let's dive right into the core concepts. Moving on to the core concepts. At its heart, a book embedding is all about mapping networks geometrically onto a physical spine and discrete pages. Instead of looking at a graph as a random web of intersections, this concept forces us to rethink its geometry. We take the abstract components of a graph, the vertices and the edges, and embed them into a structure that looks exactly like a book. To do this, we rely on two fundamental elements: a single linear line, which acts as our anchor, and multiple separate half-planes that branch out from it. Let's look at how these components actually work in the next slide. So, what is a book embedding? To break it down simply, this embedding process consists of two primary components: the spine structure and the page assignment. First, let's look at the spine structure. In this step, all vertices in the graph are ordered and placed along a single line called the spine. This creates a strict linear ordering of the nodes, meaning every single point is lined up perfectly like passengers in a queue. Second, we have the page assignment. Once the nodes are locked in place, each edge is mapped onto one of the half planes or pages sharing that same spine. By separating the edges across different pages, we distribute the connections evenly to prevent cluttering and avoid intersections. In short, the spine acts as our base anchor, while the pages give us the clean layout we need. Let's see the specific elements that make this work in the next slide. Now let's take a closer look at the three core elements that define this layout. These are the spine, the pages, and the arcs. First, we have the spine. This is the shared boundary line serving as a central axis where every single vertex must lie. You can think of it as the foundational backbone of our entire graph structure. Next are the pages. These are a set of semi-planes extending directly from the spine, acting as distinct routing sheets. They give us the extra dimensions or layers needed to separate our network components. And finally, we have the arcs. These are circular curves drawn on individual pages to represent connections without overlapping. Instead of straight lines crossing randomly, these neat curves ensure that everything connects smoothly on its designated page. Together, these three elements allow us to transition from a messy network into a highly organized structure. Let's move on to see the next section. Now we come to the most critical part of this layout, which is the crossing constraint. To make sure our book embedding is valid, we must strictly follow the safety rules. The core rule is this: two edges residing on the same page cannot cross each other. Mathematically, for vertices ordered sequentially on the spine, such as the condition u less than x less than v less than y, if the edge uv and the edge xy cross, they must be allocated to separate pages to resolve the crossing. As you can see in the illustration on the right, when a network becomes too crowded and lines start to intersect, we can't keep them on the same layer. By moving the intersecting edges to a different page, we completely eliminate the clutter and keep the entire system clear and crossing free. This constraint is what drives the need for multiple pages. Let's see how we measure the total pages needed in the final section. Finally, we reach the ultimate goal of this concept, which is defining book thickness. Mathematically, this is represented by the notation you see on the left. Beta of G, which measures the page number complexity. Our main objective here is minimizing routing layers. The book thickness, or sometimes referred to as the page number, represents the absolute minimum number of pages required to achieve a completely crossing-free layout for a given graph G. Essentially, it acts as a primary index of how intrinsically parallel or multi-layered a network's connections are. The lower the book thickness we can achieve, the more efficiently we can route the network without any intersections. And that concludes my presentation on book embeddings of graphs. Thank you so much for your time and attention. Now, let's take a brief look at the historical milestones and see how this concept evolved over time along the timeline. It all started in 1973 when Ullman first introduced the concept of stack layouts for networks, which laid the very first foundation for embedding graphs. A few years later, in 1979, Bernhardt and Kynan formalized the mathematical limits of book thickness, giving us a clearer framework to work with. Then, a major breakthrough happened in 1986 when Yannakakis mathematically proved that all planar graphs require a maximum of only 4 pages. And finally, from 2007 and beyond, researchers proved that finding exact page thickness bounds is actually an NP-complete problem, meaning it remains one of the most challenging and complex computational puzzles in modern computer science. Knowing the history helps us appreciate how important this structured format is for analyzing complex networks today. Next, let's explore an interesting connection between this topic and computer science, specifically regarding stack sorting and permutations. First, let's talk about stack equivalency. Placing edges onto distinct pages in a book embedding is actually mathematically equivalent to routing data elements into discrete last in first out structures, or what we commonly know as stacks. This brings us to data streams. This concept becomes incredibly useful for analyzing permutation streams, where items or data packets must be stored or reordered dynamically in real-time system environments. And finally, this extends directly into complexity theory. By understanding book embeddings, we can directly connect graph parameters to memory space constraints in Turing machines, helping us measure the true computational limits of an algorithm. So, as you can see, this isn't just about drawing abstract shapes. It has a profound impact on how we optimize data processing and memory structures. Now, let's look at one of the most prominent real-world applications of this theory, VLSI chip architecture, specifically in microchip routing. In VLSI design, managing hardware complexity is a huge challenge. Interestingly, the spine layout we discussed earlier perfectly matches the physical rows of components on a microchip, while the pages correspond directly to the physical layers of the microchip itself. By minimizing the page count using book embedding principles, chip designers can directly reduce physical layer demands. This is a massive advantage because it cuts manufacturing costs and significantly boosts computational throughput. As you can see in the microchip rendering on the right, keeping network routing structured and multi-layered without overlaps is exactly what allows modern hardware to be so compact yet incredibly powerful. Let's transition to our next section to see where else this mathematical concept is applied. Now, let's look at how different graph structures affect our book thickness requirements on this slide, titled Page Needs by Structure. As a general rule, standard tree and cycle graphs can be routed in a single stack page. Looking at the data chart, we can see that simpler networks like trees and paths require only one page. Similarly, closed loops or cycles, C sub n, are also highly efficient, needing just one page to be cleanly embedded. However, as the network structure becomes more elaborate, the topologies scale up. For instance, planar 2 trees double the requirement, demanding 2 pages. And finally, when looking at all planar graphs as a whole, the complexity maxes out, capping strictly at 4 pages, which beautifully links back to the historical milestone we mentioned earlier. This chart clearly proves that the structural layout of a graph directly dictates how many layers or pages we need to resolve our connections.